U-substitution is a concept of integral calculus used to reverse the chain rule. Essentially, it allows you to replace a long, drawn-out equation with a variable, u, in order to make integration easier. Let's look at our first example so we can go over the basic concepts of U-substitution. Our original equation is going to be the integral from 1 to 2 of the natural log of x over x dx. First, we have to decide which part of the equation looks like it has the most going on, because usually that complicated part can be substituted with something easier. It looks like in this problem, the variable u should substitute the natural log of x because it's the busiest part of the equation. This part, figuring out which aspect of the equation should be replaced with u, can sometimes be tricky. But with practice, you'll begin to recognize derivatives and patterns that let you choose the perfect value for u. So, we're assigning u the value of the natural log of x. And now, we need to take the derivative of both sides in order to find du. Now we have to decide what's the derivative of natural log of x. Well, we need to rely on our prior knowledge a little bit, and we know that the derivative of natural log of x is 1 over x because it's a part of our basic derivative rules. So we can write this side as 1 over x dx. So essentially what we're doing here is, in order to write du, we can replace all this part of the equation with du when we integrate with our u substituted in for x. However, in this particular problem, there already is a 1 over x dx in the equation because the natural log of x over x dx is essentially the same thing as writing natural log of x multiplied by 1 over x. Therefore, this is u, this is du, and the dx is right here. So when we rewrite our integral, I'm not going to write the limits just yet, we'll address that in a second, but we can just rewrite it as u substituted for the natural log of x multiplied by du, which is 1 over x dx. So now we have our equation that we want to integrate, and regarding the limits, for this first problem, we're going to try and approach the limits that requires you to change them to adjust to the new variable. In the next problem, and in the problems following that, we won't change the limits, and those are two different techniques that you can use and choose which one is your favorite, which one's the easiest for you personally. So first, let's practice changing the limits. Well, the limits can't be the same because this is an equation that utilizes x, while this is an equation that utilizes the variable u, so there has to be different limits. It's a really simple way to just change the limits. You use your equation that you have right here, u equals the natural log of x, and just plug in these values of x and write them as your new lower and upper limits. Our lower limit on the original equation is 1. Plug that in for x in your u equation, u equals the natural log of 1 for our lower limit. And we can do the same thing for the upper limit. This is 2, plug that back in, so u, the upper limit, is going to be natural log of 2. So what we can do, since we substituted our limits and we substituted a u and du, now we can just go ahead and integrate. So how would we do that? Well, the first step would just be to change the u into u squared over 2, just by integrating. The du goes away since it's a derivative and you're taking the integral of a derivative. So now we have this equation. Use our new limits that we decided for u, which was the natural log of 1, the natural log of 2, and then you can just go ahead and plug these limits into your equation to get your answer. So you would just do upper limit plugged in here minus the lower limit plugged in here to get your final answer. Now remember, here you don't want to change anything about this equation. You can leave the u because we changed the limits. So our final answer in this situation is going to approximate out to about 0.240. And you're welcome to plug those into your calculator and see what answers you get, but this is what should be obtained by following through with these steps. Let's move on to our second equation. Let's try U-substitution with trigonometric functions. Our original equation, I'm going to keep the limits the same just for easy understanding. It'll be the integral from 1 to 2 of 2 sine of 2x dx. Okay, so to make the problem a little easier, we can first start by moving this 2 over to the left of the integral. And this is an important integral rule that really can make your integration process easier. Now, let's look at which part of the problem looks a little strange and looks different from the parent function of just sine x. This 2x right here within the parentheses within the sine function is different from what we're accustomed to seeing, is different from that sine x that we're used to working with. So we can set our u equal to 2x in order to work with an equation that's a little easier for us. So u is equal to 2x, take the derivative of both sides, so du is equal to 2 dx. And this is something that we didn't have to do in the last problem, but that we'll have to do now. There's a 2 over here, and this coefficient in front of the dx can't just be plugged in over here because we move this 2 over, and now there's nothing in front of the dx. In order to make this du equal to what's already in the equation, we have to divide both sides by 2, meaning that we're left with 1/2 du is equal to dx. And now we can go ahead and substitute. Our new integral, don't write the limits just yet, 2 on the outside. For our first step, we know we can get rid of this 1/2 by moving it over to the other side. Let's go ahead and do that. And this equation works really nicely because 2 multiplied by 1/2 just leaves us with 1, meaning we don't have anything to worry about on the outside. Now we can decide our limits. Last equation, we tried changing the limits to adjust to the new variable in the problem. Now let's keep our limits the same until the very end and see what happens. So I'm not going to write any limits right here. We're just going to integrate. So we just have sine u, take the integral of that. It's just going to get us negative cosine of u. And now that we have our integrated equation, now we can write our limits. So we're going to keep our limits the same as 1 and 2, but in order to do that, we need to plug back in our original value for u, which is 2x. All you have to do is, instead of writing u, write all of this with 2x. Plug in your limits, and that's going to be the final way to obtain your answer. And your answer, when you plug everything in, is going to equate to approximately 0.237. Now that we talked a little bit about using U-substitution with different limits and trigonometric functions, now we can try a third problem, again with trig functions, but now we're going to have derivatives that are a little more difficult. Integral from 1 to 2 sine of x multiplied by cosine of x dx. This time, when we're choosing our u, we need to consider the possibilities of our derivatives. We could go really two ways with choosing our u. If we say that u is equal to sine of x, then what's the derivative of that? Well, the derivative of sine of x is cosine of x. So our integral just would become a simple u du. However, you could also do u is equal to cosine of x. But then our equation can kind of get a little messy, because when we take the derivative of both sides, the derivative of cosine of x is negative sine of x. And since this sign is negative, when in the equation it's not negative, we know that we're going to have to work with some negatives and moving over negatives around our integral. So this could be a little trickier. In this case, this is a way for you to choose, okay, which option is going to be the easier way for me to obtain my answer, and it's ultimately going to be this one. So let's continue working out our integral using u is equal to sine of x. We have u du, and just like the first problem, we can go ahead and just do u squared over 2. The du goes away. Let's keep our limits the same, and then plug back in our value of u, which in this case is just sine of x. your next step would be to plug in the limits of integration. And when you do that, your final answer will equate to around 0.059. Moving on to our fourth example, we're going to practice U-substitution using exponentials. Here's our equation. It's e raised to the power of 5x plus 6. We already know that the integral of e to the power of x is going to be the same exact function. So we want to reduce our equation to that somehow using substitution. That way we can integrate easily. Knowing what we want our result to be, we can make u equal to this entire exponent, this whole thing. So u is equal to 5x plus 6. Take the derivative. Du is equal to 5 dx, but we don't want this 5 over here. We have to divide both sides by 5, leaving us with 1/5 du equals dx. Now that we know this, we can go ahead and plug in our values. E to the u, 1/5 du. Next up, just move this 1/5 over, move it to the outside, and then for this problem, for the purposes of just ease of understanding, we'll keep our limits the same and then plug back in our value for u. So we've got the integral of e to the u, which we know is just e to the u. Don't forget that 1/5 that's on the outside. So this becomes 1/5 e to the u. Use our limits, but change your u back to 5x plus 6. And when you do that, and you plug in your limits, you're going to get a larger answer than what we've been getting, approximately 1.765 times 10 to the 6, which makes sense because we're working with exponentials. And remember, exponentials just continue going up in a vertical direction. So that makes sense that we get a very large number. Finally, our last example will practice U-substitution using two separate terms that are multiplied together. Kind of a culmination of everything we just went over. X multiplied by e times 6x squared plus 5 dx. This is another one of those problems where seeing what to set equal to u just becomes easier with practice. We know that if we take the derivative of this exponent, it will become a function of x instead of x squared. And we can see that that matches this variable structure, this x, of another part of the equation. However, as you can see, we're going to have a coefficient that must be accounted for. So let's walk through the steps. If we set u equal to 6x squared plus 5, take derivative of both sides, and just like we said, use the power rule to get 12x dx. So now that x matches this x up here, but we have to get rid of that 12. Divide by 12. That leaves us with 1/12 du is equal to x dx. Now conveniently, this x dx we can see in the rest of the equation. We've got e to the u, so the equation that we're substituting u into, and then x dx can be accounted for if we write 1/12 du. So let's write our new integral. We've got e to the u, and then 1/12 du. Move this 1/12 over to the outside. And now for our limits, we'll keep them the same. E to the u, the integral of that, is just e to the u. Now, finally, we have to plug back in our value for u, and it's kind of long here, this whole equation. So you would write 1/12 e to the power of 6x squared plus 5 between the limits of 2 and 1. Just plug those in, subtract, and your final answer will approximate to about 3.276 times 10 to the 11th, which again makes sense because we're working with exponentials. So let's go over the basic steps of U-substitution before we wrap up. First, identify your U. Second, you're going to write your equation, U is equal to some part of the equation, and then take the derivative of both sides to find your value for du. And sometimes you're going to have to divide and do different things, so your value for du might be 1/2 du or 1/12 du just because of some coefficients that need to be accounted for. Plug in. So this is substituting. So this is where you would plug in your value for u, your value for du, and ultimately integrate. Finally, once you've gotten your integral, make sure to plug back in original values of x. So whatever's equal to u. Like if u is equal to 2x, you would have to plug back in 2x anywhere you see a u. That way you don't have to worry about changing your limits, and you could plug those limits in and ultimately find your answer. So remember that U-substitution is a handy way to reverse the chain rule, and it's something that's important to know when taking integrals.